Welcome to another AQA A-level chemistry video. Today I'm going to make a video on understanding nuclear magnetic resonance. So this is now going to come up to the last section of year 2 organic chemistry. I'll be doing, after this I'll be doing exam questions to do with year 2 organic chemistry. And yeah, but so first with NMR, give a small introduction to NMR. It's a one type of as there are many types of physical types of ways to identify it's a way to physically identify what type of compound that you have. Is you have to start becoming more familiar with it, because it's a type of it's much more accurate compared to say, well, say you use it alongside other methods of identification, such as infrared and what is the other ones, mass spectrometry and all sorts. But really, this is the best way of understanding not only the type of not only the type of functional group that you have, but also the shape of the molecule, and giving you actually a very good understanding of what the compound actually is, any side chains that you have, how long the compound is. Whereas other types of identification may just give you an understanding of what type of compounds it may be, what type of functional group it may have. But although this is the best way of giving you the best way of sorry, as though this is the most detailed way, or this gives you the best way of understanding your compound, other tests will be done, such as IR or mass spec, alongside of NMR, all together that helps you to give a more accurate understanding of what compound you have, just in case you may have any inaccuracies. So if you've tested for NMR that you know you have an alcohol, it's also more encouraging saying that if you've done an IR test, and it also gives you an alcohol, so it just gives you it just makes the results more reliable, if that makes any sense. But in your exam, at least what matters most in your exam, you're not just going to get just NMR, although it's quite a big part, and it can be, arguably this is one of the most confusing parts of organic chemistry, and probably one of the most confusing parts of all chemistry, being really honest. It carries the most marks. So don't get too confused if you don't get it at first sight. I never got it at first sight. I kind of clicked on it and I kind of worked on it multiple times. And the best way to handle this type of question is to do multiple practice questions on it. But going back to what I said before, you're not just gonna get, even in the exam, you're not gonna get just NMR. You're gonna get, so the main ask, the whole idea is you identify what compounds you have, and I'll give you an IR sheet, so an IR data, an IR graph showing you the infrared spec of sorry, not graph, infrared spectra. Sorry, I can't get my words out. It gives you infrared spectra of a compound, as well as may give you, they may not give you necessarily mass spec, but they'll give you other types of identification or other types of graphs to help you alongside giving you the NMR graph, which I'll go through. It could be H1 or C13. I'll go through them all here down here, but most important is that you understand that you don't get too confused, that all the information there is to help you. They're not trying to like trick you too much with giving you more than one graph. Technically, getting more than one graph helps you make a decision much better. So look out for this. These type of questions can throw you off if you don't know what they're actually testing, what you have to. If you don't know what they're trying to get across to you, then this won't make any sense to you. But try and understand mostly first. But once you get the basics of what's going on, that's fine. But if I'm being honest with you, they never really ask you about how NMR actually happens. In my experience, they never really ask you how NMR happens. This is a video on understanding NMR, but it's just good to have a basic understanding of how it works, because you may get some small 1 mark or 2 mark questions on this, but then most, like the 6, the 7, the 8, the 9, I think I may have at least, there's definitely a 10-mark question I've seen at least once on an NMR question, and those questions are just about you interpreting an NMR graph and being able to use that graph to draw out a compound, because they'll ask you to draw out or explain a compound and be able to know what the compound is from the NMR graph. Anyway, though, enough of me talking. I probably talked like 5 minutes straight now, haven't I? Um, but yeah, basic principles of NMR. So nuclear magnetic resonance, or NMR spectroscopy, uh, is a widely used analytical technique for the characterization of organic compounds. So information given by NMR spectra. So an NMR spectra gives information about the environment and positions of hydrogen and carbon atoms in a molecule, and this makes it a very powerful analytical tool for chemists. So NMR gives information about position, but also the environment that hydrogen or carbon atom is in. I say hydrogen and carbon atom. It can be for others, but it's generally for the ones that we generally use are a specific group of hydrogen and a specific group of carbon, and I'll explain why later on. So overall spin. So in NMR, we can only analyze nuclei that have an overall spin, and these are nuclei that have an odd nuclear number. And a nuclear number is just equal to the number of protons plus the number of neutrons. So it's just the relative mass number, right? Not the atomic number. Um, so the relative mass number, or AR, is the same as the nuclear number. The amount of subatomic particles that you have in your nucleus, not the atomic number. So the RFM here, the mass or relative mass of helium would be 4, or the AR, or the nuclear number of helium, would be 4, whereas the atomic number, which is just the number of protons, would be 2. We're not looking at that. We're looking at the nuclear number. And for NMR, for it to have an overall spin, it needs to have an odd nuclear number. So helium can't be used for NMR because it has an even nuclear number. But say carbon 13 and hydrogen 1 are both examples of such nuclei. This is why these isotopes are commonly used for NMR. The nuclear number of carbon 13 is 13, and the nuclear number of hydrogen 1 is 1. So carbon 13 has 13 has a relative mass of 13, and the uh, nuclear number of hydrogen, or normal hydrogen, is hydrogen 1. Now, carbon 13, of course, is an isotope of carbon. Its nuclear number is 13, which is why it's beneficial for NMR. 6 protons, obviously, but 7 neutrons. But the reason why this is less used, although it's used in your exam, you don't need to worry about this. I'm just talking about in real life. In the exam, assume that carbon 13, you don't have to know about carbon 13 is less used than another type of NMR. They'll just ask you the questions. But just for general, just me being able to just give you a little bit of information. Carbon 13 is obviously it's an isotope of carbon 12, so isotope of carbon, and the one that we usually understand, the normal carbon that we all know of, is carbon 12. So that's why it's less used compared to, you have to actually form the isotope, more or less. You have to form the isotope carbon 13 and then use it for carbon 13 NMR. And then you have to the carbons of that compound have to have carbon 13 NMR. Whereas hydrogen, the normal isotope for the hydrogen, let's say not normal, the most abundant, I shouldn't say normal, the most abundant isotope for carbon is carbon 12, hence why carbon 13 is less used in NMR, simply because you have to actually obtain carbon, as the compound that's in your, let's say you want to do NMR for ethane, right? All the carbons in ethane, or let's use a larger example. Let's say let's go for like a 10 carbon long, some sort of 30, or let's say a 50. Let's say you had like a 25 carbon long compound, right? It could be possible. You could have that, right? And you want to do the NMR investigating that 25 carbon long alkane, for example, right? I don't know the name of it, but you get my point, right? All of those carbons would need to be carbon 13, and for that NMR to work, if you know what I mean. So it wouldn't be able to detect a carbon 12 because it has an overall spin, whereas hydrogen 1, because hydrogen 1 is the is the most abundant isotope of hydrogen. Deuterium and tritium are very rare. So hydrogen 1 is more used, or it's type of NMR that's a bit more sought out. But to be honest, in your exam, they could give you carbon 13 or H1 NMR. They're not looking for you to explain that. I just wanted to just say that out loud, maybe give you a bit of information about it. But really, honestly, you just need to know that carbon 13 NMR and H1 NMR, the two types of NMR that you'll know for your exam, because they have an odd nuclear number, and because of that they will have an overall spin, and they'll be used for NMR. Now, external magnetic field. So in NMR spectroscopy, we place a sample substance into a magnetic field, and as you said, the nuclei of a substance have an overall spin, and this means that the nuclei are each very small magnetic fields of them. This means that the nuclei are each very small magnetic fields themselves, and a nuclei can interact with an externally applied magnetic field that they are sitting in. So, the overall nuclear spin can either spin with or spin against the external magnetic field. So, say this value is representing our external magnetic field. So, if we apply some sort of external magnetic field, the overall spin is going in towards this way. So nuclei, there could be some nuclei, or say there'll be either or. There'll be either nuclei that's going in the direction of the magnetic field, of the externally applied magnetic field, spinning in that direction. And this blue arrow here represents the overall spin of the magnetic field. But there will be some nuclei that are going against this overall spin, right? And all of these nuclei, as I said before, have a very small magnetic field themselves. Now, the NMR theory is that we now consider what causes the signals to produce. We will now consider what causes the signals produced in the NMR spectra. And remember, the NMR can either be H1 NMR or carbon-13 NMR. Nuclei in a magnetic field. So the nuclei sit in a magnetic field, and some of their overall spins will spin with the magnetic field, and some will spin against the magnetic field. So we call whether they spin with or against the fields different spin states. So the nuclei that are spinning with that magnetic field, that externally applied magnetic field, are lower in energy compared to nuclei that are spinning against the externally applied magnetic field. They have high energy. So if to actually go against the overall spin of the externally applied magnetic field, that requires much more energy. And those are regarded as being higher energy nuclei compared to ones that spin with the magnetic field, compared to they're known to be lower energy nuclei. It's energy difference. So the nuclei can exist in either of two spin states, which are of different energies. So energy must be gained or lost for a nucleus to change its spin state, and we say there's an energy gap between the two spin states. So the different spin states, right? So lower energy level, that's one spin state, and any upper energy level, that's another spin state. But in order to get to that higher energy level, you can change your spin state. You can go from an atom with low energy that follows the magnetic field. So let's say this is the external magnetic field. So ones that have lower energy level would go in the direction of the external magnetic field, but those that go against, if you breach or reach this, kind of think of it like an activation energy. So activation energy isn't just that one example of reactions. Activation, there's different types of activation energies as I'll go into year 2 physical chemistry. There's different types of activation energies, but one of them here is just when we're talking about energy gaps. When you reach that energy gap and you reach the upper energy level, you now have energy to change your spin state so that your nuclei is spinning against that magnetic field. Now, all of this nuclei spinning and all of this, it's kind of confusing for some people, and there is a reason why we measure this and how we're able to measure this. So I'll go through that. Hopefully you follow me. If you don't really follow me, or if you don't get what I was up to here, stick around as I go through the rest of this video. But if it still doesn't make sense at the end of the video, leave a comment and I'll try and explain it a bit better. The energy gap. So the energy gap between the two spin states corresponds to energy in the radio frequency region. So this energy gap, the two spin states correspond to energy in the radio frequency region. So we use radio waves to change the nuclear spin state of the nuclei, right? So these energy gaps can be related to with this radio frequency region, and we can actually apply radio waves to actually change the nuclear spin state. So we can use energy released from radio waves to change the spin state of that compound to a higher energy level, and then therefore we've changed the spin state of that nuclei. NMR signals. So that being able to transition between the nuclear spin states appear as they would also appear as signals in an NMR spectrum. So in H1 NMR, the signals represent H1 nuclei. I say H1. H1 just means hopefully you know what I mean the isotope. Same as the same me saying carbon-13. H1, hydrogen-1, and carbon-13. So in H1 NMR, the signals represents the hydrogen-1 nuclei transitioning spin state from different environments, and a carbon-13 NMR, it signals represents the carbon-13 nuclei transitioning spin states from different environments. So the transitioning, so once you apply that radio frequency, and I could probably should I get no, I'm not gonna get it. You need to know what it looks like. But these are massive machines that they use for NMR. They're not like small like in a lab. Like they're usually massive components. And so that's how, and what we're doing here is that we're firing in those massive components, we're firing radio waves at these nuclei to actually so that they breach that energy gap and they change spin states. And now in H1, they're actually transitioning as is breaching that energy gap. That's actually the transitioning period. And transitions between nuclear spin states appears, they also would appear as signals in NMR. We're able to read the transitioning of spin states. And those appear as signals in the NMR spectrum. Now in H1 NMR, the signals represent, so in hydrogen 1 NMR, the signals will represent the hydrogen 1 nuclei transitioning spin states from different environments. So those, as I said in the beginning of the video, all hydrogens are in different environments. But what I mean by environment is, let's say a hydrogen that's next to a carbon next to another hydrogen, that's one spin state. That's one environment. But if you have a hydrogen that's bonded to a carbon that's bonded to a hydroxyl group, that's a different environment. Because when I mean environment here, environment is the condition that those atoms are in, and usually it's the condition of the carbon that's bonded to another group. So because obviously a hydrogen that's bonded to a carbon would experience a different type of attraction compared to a carbon that's bonded to a hydroxyl group. Obviously that hydroxyl group is much more electronegative. So it's a different environment. So if a carbon that's bonded to a bromine experiences a completely different environment to a carbon that's, so a hydrogen that's bonded to a carbon that's bonded to a bromine experiences a completely different environment to a hydrogen that's bonded to a carbon that's bonded to, say, a cyanide group or or an amine group, right? And that's what I mean by environment. And so when we're so now that I've brought it here, we're measuring the transitioning in spin state of the nuclei on the hydrogen that's bonded to that carbon, right? So we're talking just about that. If we're talking about hydrogen, let's forget about carbon-13. The same thing applies to carbon-13, but let's say we're talking about hydrogen-1, right? We'll talk and let's say had this compound here, carbon. Oh, I can't even go down here anymore. And let's say a cyanide here, right? This is one type of environment that this hydrogen is experiencing. This hydrogen is experiencing in this environment. Now this is a different environment. Now we're talking about the hydrogen here. We're talking about oh, that's not why I done that. That's weird. What's that? We're talking about this hydrogen here. Well, I guess both of those hydrogens here, right? Now let's say this is on the same molecule, or they could be on different molecules, right? But say we have of one. We're measuring one molecule at a time. We're never trying to do two molecules at the same time, right? These hydrogens are in different environments, and the energy gaps will be slightly different. And when they're transitioning between nuclear spin states, they would appear as different signals in the NMR spectrum because their energy gaps would be different. The amount of energy that's put in, it would be from the radio waves would be different. And we're focusing mostly on the hydrogen, the nuclei of this hydrogen here, and they would experience a different to reach different spin states. They would have to have different energy gaps, right? this would be different because they're in different environments, and hopefully, and we're able to pick up and read, and be able to also what kind of word we're able to measure those different signals as on the NMR spectrum. So when it's transitioning between different nuclear spin states, that energy gap, the amount of energy put in, we're able to measure that, and then measure those signals, and we know that those signals represent, over time that we've collected data now, we're able to identify that those specific signals represent different type of hydrogen environments. So if it's a hydrogen that's bonded to a cyanide, hydrogen next to a hydroxyl group, and that's what we're measuring here, right? And it's the same thing if it was carbon-13 NMR. So say this was a carbon-13, we'd be able to measure that as well. So it's measuring the transitioning of spin states sorry, I'd say again, we're measuring the transition of spin states, or the energy gap as it's transitioning between spin states on the nuclei of that either carbon-13 atom or hydrogen-1 atom, the nuclei. Alright, so different chemical environments. So the exact energy and frequency of radio waves needed to change this nuclear spin state is different in different chemical environments. So different NMR signals represent nuclei positioned in different chemical environments. In H1 NMR, each signal represents hydrogen 1 in a different chemical environment, and in carbon-13 NMR, each signal represents a carbon-13 in a different chemical environment, like I said before. Right, and this is what it's here. And so when we're measuring this different energy gap here and different transition, that gives us a different. This is an example of hydrogen 1 NMR. I can tell you why as I go through. I'll be making multiple videos on NMR, but I can tell you why, because of it's got peaks, multiple peaks on one peak, singlets, doublets, triplets, and but I'll be going through more of this in detail. But yeah, but these peaks here are represented by the type of these are the signal readings that we're getting for the different energy gaps, the amount of energy that needed to put in to actually cause this peak, right? So that's what we're measuring here. We're measuring the exact energy and frequency, not just energy and frequency of the radio waves needed to change the nuclear spin state, i.e., to breach this energy gap, i.e., change from here to here. Hopefully that made sense. And then once we've done that, we're able to measure that and put it on a graph here, and then we can use this graph to determine what environments that we have. And if we know that it has specific environments, so this is a hydrogen bonded to a carbon next to a hydroxyl group, whatever, we're then able to put those different groups together. And then, like this group here, so say this is the only two groups that we had, we can clearly tell that the overall look of this group would look like something like this, right? Oh, don't know why that happened, but don't know why this happened for some reason. That and an OH. Right, so this is, so if we had only these two peaks, and we knew it's only these two peaks here, and so if we looked at our graph, and we looked at the graph and we compared to our reference, by the way, in your lab books, not lab books, in your data sheet, there'll be a data sheet for all the different types of peaks in your NMR spectrum, so you don't have to just know these off by heart, like this is a hydroxyl group is, say, up to 0.9 whatever. There'll be a data book to help you, and you just need to look and say, oh, my data book, it says this. Like with IR, like with infrared, you don't need to know every single infrared. Some of them you kind of know by memory as you keep going on, but you have the book there. But it's just to look at the graph and say this is on 3.6, something like that, or 3.7. What does that say on my reference? That means that represents a cyanide group, for example, right? There is a way of actually understanding why they move progressively towards progressively higher, but that's for another video, I assume. But being able to say that we know that this is a cyanide group, or this we know that's a hydroxyl group, and say, okay, we have only those two peaks there, right? If say this is the only two peaks that we have there, we know that this is the chemical that we have here is a 3-hydroxypropanitrile. Seems simple enough, right? And that's how we actually do it. That's how we do it. Now, obviously, it's a lot more complicated like that. This is a very easy example if it's only these two here, but if you get like you can do this for cyclo groups, and cyclo groups are kind of the hardest to kind of see sometimes, or like long chain carbon or multiple chain groups, but yeah, that's what you have to be worried about. This is what this part here, actually being able to identify what the compound is from the group. That's where you get the most marks. The most marks for. That's the type of question that comes up with the most marks. But just giving an understanding of how this actually happens, and then what we're actually doing with that information. Now, chemical shift. So in NMR spectra, displays signals at specific chemical shift values. That the chemical shift is the value that appears on the x-axis of the spectrum. So like I tried to show you before, so that signal is before. So we're measuring the different energy and frequency of radio waves needed to change the nuclear spin state, and then that's what comes up as a signal here. Now we represent that signal by something called chemical shifts. So the NMR spectra displays signals at different chemical shift values, and the chemical shift is the values that appear on the x-axis of the spectrum. NMR signal. So as you've seen, a transition of nuclei between spin states causes a specific signal. So nuclei in the same environment will provide the exact same signal. Right, so one thing they need to know, right? So as I said before, I've just explained to you that the spin states are specific for specific type of compounds. But say you had the exact same environment on a molecule, right? So if you had the exact same environment on a molecule, they would overlap. It would be in the exact same position. Now, what I mean by that is, like, let's say you had, if you had two graphs, right, and you had to split the compound in two, so you wanted to do this side of the molecule and this side of the molecule, but if they had the exact same environment, right? Let's say methane. Let's say methane, right? I was trying to get the environment of one carbon hydrogen, another carbon hydrogen, another carbon hydrogen, another carbon hydrogen, and we did the NMR of that, right? And I put them as let's say four graphs, and I was doing the exact same thing, right? And I put all the graphs on top of one another, and they're all see-through graphs. I'd be able to see that they all exactly line up with one another. They all align. They all overlap to the point exactly above one another. Why? Because they're in the exact same environment. So hydrogen's in the exact same environment. Hydrogen 1's in the exact same environment, or carbon 13 is in the exact same environment will produce the exact same signal in the exact same position. So in saying that, we technically can't say for certain how many molecules we have, because we can measure the amount of hydrogen ones by the area underneath the graph. We can integrate the area underneath the graph to tell you how much hydrogens, but you don't know we don't know how many of them are in the exact same position, because they overlap exactly over one another. That's the only thing that we don't know. But the good thing is that we're not really looking about how many molecules do we have. That we're looking about identifying what type of compound that we have. How many molecules we have, we can just do another type of method for looking at that. One way, as I said before, is that the area underneath the graph represents. If you integrate this area here, and you're able to find the area. If you integrate this graph, sorry, I should say integrate the area. It doesn't make any sense. If you integrate this graph, you can find the area underneath the graph. That's what I meant. Sorry about that. Sorry about the confusion. If you don't know about that, don't worry. It's something that comes up in maths. You don't need to worry too much about that. Just a little fun fact, I guess, on the side, that if you integrate the graph and you manage to get the area underneath the graph, that represents how much hydrogen ones that we have. But you never have to do that for chemistry, unless you go for a high level in a university. But just a little side thing there. But all you need to know is that if a hydrogen one is in the exact same environment, so if we have a long carbon, right? Say we had pentane, right? Realistically, we're looking at, we'd have certain ways to kind of identify, but a lot of those bonds that you have, the carbon hydrogen ones, that because they're in the exact same environment from one another, the graph would overlap. You know what I mean? So certain peaks would just overlap over one another. Knowing how many we have is a different way of doing it, and I'll go through that in different videos. But the environment is the exact same environment. Hopefully I made this clear. Hopefully it didn't confuse you. If it's in the exact same environment, they'll overlap one another because because they'll be in the exact same position as one another. So if one peak is like this, if one peak's like, if you've got same thing in the exact same environment, then it'll be obviously much more neater than that, but they'll exactly overlap one another. You wouldn't be able to tell the difference, unlike mine. Great. So chemical shift. So a signal appears on the spectrum at a specific point on the x-axis, and this is the chemical shift value. Nuclei in the same environment will produce a signal at the exact same chemical shift value. The chemical shift value is along this x-axis here. As I said before, it will produce it at the exact same chemical shift value. And overall, when we read the spectrum, we can say that each different signal of a particular chemical shift along the x-axis represents a nucleus in a different environment. So if it doesn't exactly overlap one another, it means that they're in a different environment. So if they're in the exact same environment, they'll overlap. But if they're not, even if they're slightly different environment, they won't be in the exact same position. That's all it means. Chemical shift notation. So the sign for chemical shift is delta, and the units for chemical shift is ppm, which stands for parts per million. Now the table of chemical shift values for H1 and carbon-13 NMR has been made, and it's actually given to you. If you look to your data sheet, you'll see a massive, you'll see this part here. So this is for you have your infrareds here. So this is your infrareds, and you notice sometimes for AS, you're only given that because you don't need to know about NMR. But for A level, you need to know about this as well. And this is given to your exam. You just need to look at your graph and say, where peak, this peak here, right? So if it says between 0.9, right? So it's roughly 0.9-ish. What could that possibly be? There's a lot range compounds here. OH, CH3. So maybe it's a CH3. It's got multiple carbons. Maybe that's it. 0.7 to 1.2. Now being able to read and understand why the graph has 3 peaks here, for example, in H1 NMR, I'll get onto you, and you have to be very specific about that. But this is kind of like an introduction to understanding nuclear magnetic resonance first and how it works and what you'll be kind of looking at. Hopefully this video was useful, and that is it. Subscribe if you did find it useful, though, at least.